Okay, so good afternoon, everyone. It's 5:02, and I'm going to start the class. Okay, so give me a moment to share my screen first. Okay, hold on. Okay. So if I recall the last meeting that we have, which is I think which was last week, we were learning about balancing the chemical equation. And now I think on the last meeting, I was trying to solve this question. I think because there was like a time, I think I had a meeting that day, and I promised that I will solve this question for today's meeting. So okay. So since I think we're still on chapter one and trying to go fast, I'm not going to answer all. I'm just going to pick two questions out of these three. So now we're going to do that. So first of all, I'm just going to let's say that we're going to pick 12A. So we are going to identify first the symbol for each compound. So first of all, we have iron. We have iron, so iron would be Fe. I'm just going to write it here somewhere. Okay, that's way too far. Okay, here. So I'm going to write it down here first. So we have Fe. So usually they will write if it's solid or not, but iron is solid, so there usually a small parenthesis S, usually. I'm going to write it down manually. And then it reacts with hydrochloric acid, meaning that it will be a plus, since it reacts with each other, so that will be plus. So that would be HCl, which is hydrochloric acid. So I think all of you will sort of like remember bit by bit. Back when I was still learning chemistry back in high school, I also didn't quite remember all of this compound, but actually can identify like really easy when we saw the periodic when we checked the periodic table. For example, hydrochloric, we know that hydro here stands for hydrogen, which is explain the H right here. And then chloric would be for chloride. So there you have Cl right here. I mean fluorine, sorry. Okay. So this is the first one. So we know that hydrochloric acid it's um liquid, or usually it's aqueous, something like that. How you pronounce that, not really sure, but here right here we're trying to write as right here. It's actually below Fe or iron. This is just to so that we know that Fe here or iron is a solid, it's in solid form. Here we have we have liquid, so we actually use this aqueous. So this is AQ as the symbol. AQ right here. There we go. And then it is to form. So when we say to form, meaning that this is the reactant, and then right here, the forming one. After we write it, after we draw this arrow, this will be the final product. And for the product, it says right here, which is iron 2 chloride. As you can see, it's actually written right here, so we don't really have to check twice. I'm going to type this again. Here. Okay. I'm going to add plus right here. And now we have hydrogen. And hydrogen is this, sorry for that. Hydrogen, usually when it's compound like this, it has two here. Followed by two that has two hydrogen atom right here. Can write two right here. There we go. So here it is iron chloride. This is in liquid form, or we call it aqueous. So the symbol is the same. Basically, we're going to write. Okay, I just prefer writing the Q first. Okay, that is really sloppy. Okay, I want to erase this. So we write two next to Cl. And now we're going to add aqueous right here. And this is Q. I hope you can understand my handwriting. So this is like AQ. Technically, I'm just like really bad at writing it. Okay, I'm just going to see if I can actually just type this in and actually make the words smaller. So this is technically something like this. Okay, so that's basically what I want to write. And usually it's not really like you have to memorize this, but when we are trying to write this kind of equation, they're usually this kind of symbol. I'm going to write it down. So S is for solid. And then we also have AQ, meaning it's usually like this. Aqueous, I think. Aqueous. There we go. Meaning that it's liquid form. Sometimes we can use L for liquid, but this is way more common. Usually aqueous, it's more like liquid, but it's in a compound form. I think that's it, but we tend to use aqueous more than liquid. And G stands for gas. So hydrogen here is gas. So we gonna have to write this down again. Go, just can't type. I don't want to type this in. I think it's still looks better. Oh yeah, actually I can do this. Okay. So there we go. Yes, right there. So now we're going to check if this reaction, I mean this equation is already balanced or not. So we're going to see this one by one per atom right here. And also if you have any questions, just don't hesitate to ask. You can just ask right away. Okay. So first of all, we have iron here, which is Fe. We have one iron compound right here. And then, okay, so let me just correct this a little bit to avoid confusion. So we're going to erase the two right here. And now we're going to add another two right here. So the two right here is supposed to be right next to Cl, or you can say it's chlorine. It's right next to chlorine, okay? So yeah, it doesn't count for Fe to be 2. It's only for chlorine itself. So we have one Fe right here and then one Fe right here, or one iron on both sides, left and right, or you can say product or reactant. So meaning that iron is balanced already. So we don't need to make any changes for that. Now we're going to look at chlorine first. Okay, we can actually, okay. Oh yeah, I almost forgot. There's hydrogen right here. I'm so sorry about that. Okay, so we're going to see this like one by one. So we have hydrogen right here. We have only one, but we have two hydrogens on the right side. So seeing this, we know that this equation is not balanced. It is not balanced. And when this is not balanced, we need to add something in front of it. So that's why we are going to add two in front of hydrochloric acid or HCl. So now we have two hydrogens on the left side, and then we also have two hydrogens on the right side. So now it's already balanced. And now we're going to check for the last one, which is chlorine. So when the number is right in front of the compound, it means that all of which is also has two of that. So chlorine, we have two of them since we have the number two in front of hydrochloric. And then for the second part right here, which is on the right side, we can see that chlorine right here is also two. So now the left and right side has both two chlorine, and now this is balanced. So this is basically the end. I mean the result. This is the balance equation for question number 12A. So do you have any questions so far? Okay, if not, I'm going to move on to the next question. Okay, so we're going to move on to either B or C since we don't really have much time and we've been stuck in chapter one for quite a very long time. So I'm going to see which one to not wait. Okay, so we're going to go for number C. We have hexane right here. Burns in oxygen to form carbon dioxide and water. Okay, so we're going to go through this. So we have hexane right here. It's already written, the compound, which is C6H14. So we're going to write it down. So we're going to write the C. Okay, that's too small. I'm going to make the letter bigger. Okay, that's too big. Okay, so we have C, H right there. And now we're going to plus. So plus technically means when the two compounds react each other with each other. So right here on question number C, we know that hexane burns in oxygen. So meaning that hexane reacts with oxygen, and that's how we have the plus sign right there. So that's technically what the plus means. And now we have oxygen right there. So I'm going to write now in smaller form here. So we have four right there, and then we have, oh, it's not four. I'm so sorry, but that's actually C614. C6 team. And for oxygen, here we have two. Okay. So now we have the reactant side, um, or the left side. Now we're going to see for the product side, or you can say the right side, which is to form carbon dioxide and water. So we're going to draw an arrow, meaning that this left side, the reactants, are going to, what product will they create? So right here we know that they will form carbon dioxide. So we're going to write down carbon dioxide, which is CO2, which is a very popular compound, CO2. Okay, this looks really small. No, that's too big. Okay, So we're going to write this CO2 and water. So that would be a plus since water is also called that. Okay, so I'm going to write down the smaller part just to make it neat. I decided to just type everything down instead of going. There you go. Okay. Okay, so now we have hexane plus they react each other with oxygen to burning, and they form carbon dioxide and water. So this is the reaction, and clearly you can see it is not balanced quite yet. So we're going to make the balance to make it balanced, basically. Okay, so first of all, we're going to see, usually we are going to start at the very left just to avoid confusion so that we can tell which one has been balanced or the one that hasn't been balanced yet. So right here we have 6 carbons, but only 1 carbon right here, not balanced. So, and how are we going to make this balance? We're going to add 6 in front of it. 6 right here, 6 right here. So now it is balanced for carbon only. So we can say that carbon has been checked. It's already balanced. Now we are going to go to the next one right here, which is hydrogen. So we have 14 hydrogen right here and only 2 right here. So we're trying to find the common like factor something of number. So we know that in order for 2 to get to 14, we need to times that by 7. So that's why we are going to add 7 right here in front of the water compound. So that will be 7H2O. So when a number right here, in the middle right here, we have 2 hydrogen compounds at first, but then we add 7 right in front of it. We're going to times that number. So 2 will be times by 7. And 2 times by 7, that will be equal to 14. So this right side, like right here, is yeah, the right side will be balanced with the left side. So now we have hydrogen balance. And now we're going to check for oxygen. Okay, so oxygen right here is actually pretty complex. So far right here, okay, so this is really, really complex. Let me think for a while. Okay, so first of all, we have 12 right here, and now we have 7 right here. Oh, okay. I cannot understand right now. So this is actually a pretty complex situation. Okay, so now we know that right here we have only 2 oxygen atoms right here on the left side. And now on the right side, we're going to count them one by one. So for carbon dioxide, which is 6 CO2 right here, we have 12 oxygens. From 6, we multiply this by the 2 right here. So that will be 12. And now right here, okay, so once again, the 2 right here it only applies for hydrogen. It doesn't apply to oxygen because it's in the middle. And when it's in the middle, usually this number belongs to the left side, not the right one. Okay. So meaning that we only have oxygen right here and 7. I mean 7 oxygens. We don't have to do any multiplication. So we have 12 plus 7, that would be equals to 19, right? And now we know that 19 is a prime number. And for 2, it is not a common factor of 19. So since it is not a common factor of 19, it will be like 9.5. And usually for this kind of equation, um, decimal kind of number does not exist. So we don't use decimals. And now the only thing that we can do for this to get to 19 is to multiply every equation right here that has already been here, the one that we have actually balanced previously, to 2. We are going to multiply that. So now we have, supposedly this number should be 9.5, but since we multiply everything by 2, we will have something like this. So first of all, we're going to start by that this should be 19, since we have multiplied everything by 2. And since we're going to do a 2 multiplication, the one that doesn't have a number right here will also have 2 in front of them. So we're going to add 2 right there. There we go. So this is 19. And now 6 right here. When 6 is multiplied by 2, it will be 12. And then 7, first, let's edit this. So 7 multiplied by 2 would be 14. So basically, this is the end result for this equation. So do you have any questions so far regarding this equation? Or do you want me to explain this again? So I'm going to give you 1 minute in case you want to ask any question or you just want me to re-explain things.
No. No.
Okay, give me a second. So I'm going to move on to the next. I think there's actually another question below up to 12, which is question number 13. And 13, they have, I mean, it has two parts, A and B, but I'm going to do only one of them. So, okay, I'm going to move on. So now we're, okay. Okay, so this is like the one that I've actually written. It's actually right here below you, the using state symbols. So we sometimes find it useful to specify the physical states of the reactants and products in a chemical reaction, which is what I said previously. We can tell, I mean, like identify whether that product is a solid, liquid, gas, or aqueous. This is a solution in water. Yeah, that's why I'm kind of forgot about this. I thought it's like a solution for any kind, but yes, a solution in water. It's called aqueous. The symbol is AQ. And yes, water is actually just liquid. It's not a solution. So that's why it's L for liquid. S is for solid. G is for gas, like I have said previously. So this is basically one of the basics, the essential thing that you need to know.
What about water? Water is liquid,
Yes, it's right here. Water is liquid.
but I
So
don't even know what is AQ.
AQ is aqueous, is for a solution. So when I'm talking about solution, it's actually in a liquid form, but it is basically a compound but liquid. So that is called aqueous. In other words, it's actually a solution. But as for water right here, it is not a solution. As you can see right here, H2O. That's why it stands for liquid. But actually, most reactions that you will encounter in high school, most of them are aqueous, rarely of them like liquid. So liquid is basically in the pure form and aqueous is in solution form. So I hope that answers your question.
How to make aqueous?
Aqueous basically from two, um, what do you call this? Two chemicals usually. like in the previous one right here, we have hydrochloric, right? So it's basically from hydrogen and chlorine. And when they combine with each other, they form a liquid. And this liquid will be called aqueous since it is a solution combination of two chemical products. So that's how aqueous is born, basically.
Final question. Can we make aqueous?
Pardon? What is the question? I didn't quite catch your question.
Uh, Final question. Can
Yes.
we make aqueous?
Yes, technically I think we can since most aqueous can be made. Actually, it's actually artificial, meaning that it's actually human made. So yes, it is actually possible to make aqueous solution.
Okay.
Okay, so if you have no questions, we can move on to question number 13. But if you have any questions, it's okay. You can just ask right away and yeah. So we're going to do only one, since we are still in chapter one. Once again, we need to actually move on to the next part. So we're going to write a balance equation. Okay, so now we don't really actually have to think twice about um the form. What do you call this? Suddenly I forgot about the physical states. Yeah. Sometimes I kind of like forgot words since, well, I learned chemistry using Indonesian language, and this is actually also, we're also learning with it, doing together. Um, some words are not really quite familiar to me since, once again, I learned chemistry in Indonesian language. It's not in English. So I'm sorry if I actually kind of like mistranslate things or forgot words. Okay, so first of all, we know that here states that solid calcium carbonate. So we know that's in solid form, so we can just write as. We don't really have to think. It's already stated in the question. So calcium carbonate would be CaCO3. So we're going to write that down. So we're going to write this reaction, and then we can start balancing it. So calcium CO right here. And okay, we're going to see this one by one. So it reacts with aqueous hydrochloric acid. So we know that hydrochloric acid is aqueous since it counts as a solution and not just any kind of liquid. So like it's stated in the previous question, we know that hydrochloric acid is HCl. It's actually one of the most common and strongest acid, hydrochloric.
An acid.
Yes, it's an acid. So basically when you
That
want
means
to know,
it can
yes,
melt things, right? It can melt things.
yes, in the like if it's not diluted, it's actually really corrosive. So yes, it can destroy things as well. Yes, it can. So I don't think I mean I think that we will actually eventually discuss this acid and base. I'm not sure what in what chapter, but usually to identify whether that compound is acid or not is actually way easier than base. So whenever you see a strong acid, they usually have H right here, which stands for hydrogen, something like that. So hydrogen is basically right here, like hydrochloric. This is actually usually and like one of the indicators that it is a strong acid. So just a little bit of intermezzo, but we're going to learn about that eventually. Okay, so I almost forgot to add three right there. It's actually pretty crucial. If I forgot to add that, then the equation would not be balanced. It will be complete mistake. There we go. Okay, so now to form, okay. So solid calcium carbonate reacts with aqueous. Okay, almost forgot once again to write this one. So we need to actually add this S and then AQ right here. Since this is already stated in the question, we have to include that. Okay, so here we have it. So this is the reactant. The reactants, we have calcium carbonate and hydrochloric acid. So now we're going to draw an arrow because when it says to form, meaning that we are going to the products right here. So the products is that will be formed would be water, carbon dioxide, and aqueous solution of calcium chloride. So I'm not sure. Usually, the way I write it, it's more of the one that's heavier first. Okay, I'm not sure. Understand this. So it's basically solid, aqueous, liquid, and gas, something like that. So we know that aqueous solution. So meaning that this calcium chloride is aqueous. And calcium chloride, we're going to write this down. This is calcium chloride right here. And we could not forget this one. We have two. Here we have two. And it is aqueous. Okay, why do I caps that? It should not be caps. Okay, so we have this. And the next one we have water. And water's the liquid, okay. Since it is not a solution, it's just pure liquid. So that's the other results. Okay, now for the next part, we have carbon dioxide. So carbon dioxide, I assume that most of you already know what carbon dioxide is. It's pretty common, to be honest. Okay, we're going to move that a little bit closer. And we're going to add 2 for the carbon dioxide. So usually, how do I know that there's 2 or something like that? So basically, dioxide here for D right here, it actually stands for 2. That's why we have 2 oxygens. Okay, so now we're going to see if it's balanced or not. So it's basically so first of all, we're going to check calcium right here. Calcium carbonate, only 1 calcium. And then calcium right here is also 1 calcium. So calcium's already balanced. We don't have to do anything with it already again. So calcium check. Now we're going to see which one are we going to check again? Okay. So carbon right here, carbonate. Yeah, we can check that. We check. So carbon right here, see only once. There's only one right here. I mean, right and left is only one, so balance. Oxygen, we have 3 oxygens on the left side, and then we have 3 oxygens as well on the right side. We have 2 from carbon dioxide and then 1 from water. So basically 3 oxygens on the left and 3 oxygens on the right. So oxygen has been checked as well. And now we're going to hydrogen. So hydrogen right here, we only have 1 hydrogen, but we have 2 hydrogens right here from water. So that's why we're going to add 2. we're going to add 2 in front of hydrochloric. So now we have 2 hydrogens in the left, and then we also have 2 hydrogens in the right. So hydrogen has been checked. So since 2 right here in the front usually means that now all of the chemical things right here all has become 2, 2 of each. So we have 2 hydrogens and 2 chlorine. So we have since we have 2 chlorine, we are going to check if the right side also has 2 chlorine. And turns out, yes, we have 2. So this equation is balanced. So calcium carbonate plus 2 ACl equals CCl2 plus water plus 7. Okay, I almost forgot to include L here and yes here. Okay, so it has been completed. So this one solid, aqueous again, liquid, and gas. So far, do you have any questions or you need me to explain? And now I think we can move on to the next subchapter to this. So please let me know if you have any questions. Okay, so it seems that none of you have any questions, meaning that we can move on to the next part.
It's just like a ghost Zoom, a ghost meeting.
So we're not going to do that part since we only have like 20 minutes. So I think I'd rather discuss other things since I think it's actually pretty simple once you actually get to understand the basics of that. All right. So another reaction, we already learned basically a lot of reactions. So now we are going to discuss balancing ionic equations. So it's still on the balancing equation part, but this is more advanced and to be honest, more confusing as well. Okay, so now we have an example, which is right here. So usually ionic compounds include salts. It's stated right here as sodium bromide, magnesium sulfate, and ammonium nitrate. Acids and alkalis also contains ions. For example, H plus, which is aqueous, and then we have chlorine, which is aqueous as well. Ions are present in hydrochloric acid and natrium, or we actually say sodium actually in English. In English, it's supposed to be sodium, but in Indonesia, we usually call that as um natrium. Okay. So many chemical reaction in aqueous solution involve ionic compounds. Only some of the ions in solution take part in these reactions. The ions that play no part in reactions are called spectator ions. So this is basically theory. An ionic equation is simpler than a full chemical equation. It shows only the ions or other particles the full com sorry, are reacting. Spectator ions are emitted. Compare the full equation for the reaction of zinc with aqueous copper to superpose the Nichols equation. So this is just a theory. Full chemical equation. There you can see. I'm just going to give you guys the work example after this. So this is with charges. So with charges we have right here, we have 2 plus ion, positive ion charge, and this is a negative ion charge. So since basically the same right here as O here, we can cross that out. So this is the Anakin equation. Yeah, usually they cancel each other. That's why we are called that spectator ions, meaning that we can just eliminate that and pretend that it's not there or non-existent. So in the ionic equation, you will notice that there are no sulfide ions. These are the spectator ions as they have not changed. And then you also have both the charges and the atoms are balanced. Okay, so now we're going to the work example. Okay, I'm sorry. I was drinking a bit earlier. Okay, so now we're going to write the full balance equation. So we have magnesium. Magnesium is solid. And then here we have hydrochloric. Here, hydrochloric acid in aqueous form, magnesium chloride, and then hydrogen. So as we can see, all of this equation is actually fully balanced. So we're going to just double check. We can see magnesium 1 right here on the left side. We also have 1 on the right side. Okay, magnesium is balanced. And now we have two hydrogens on the left and then two hydrogens on the right. It's balanced. We have two chlorine right here, two chlorine right here, and then also two chlorine on the right side, meaning that chlorine is also balanced. So we're going to write down all the ions present. Any reactant or product that has a state symbol S, L means solid, liquid, or gas, or is a molecule in solution such as chlorine, CO2 does not split into ions. So take note of that. So now the reaction will be something like this. Magnesium to H plus right here from hydrogen. And then you have Cl2 right here. So now we have magnesium 2 plus. We can actually see it from the periodic table in case you forgot. Cl negative right here and H2. So we are now going to cancel the ions that appear on both sides of the equation, or we actually call that to eliminate that. Okay, it has been eliminated. So now we're going to write down the equation omitting the spectator ions. So we're going to write it down. And now this is the final result of the equation, balance equation. So actually ion equation, it's not really that complex, but I'm not sure why I actually find that really complex back in high school. Maybe because that I have to also balance the equation first. But basically, you just need to identify what kind of ion they are. Either it's positive, negative, or they have like two charges of positive or something like that. And when you find um an an ion that appears on both left and right side, then you can just eliminate that. And basically after eliminating, you're actually done, actually. It's balanced already. So, okay, so for the second work example, so we have another full balance equation, 2 chlorine, 2 potassium, 2 bromine, basically fully balanced. So the ion presence, we have Cl2, okay, K plus, potassium should be a minus, meaning it's negative charge. Uh, Bromide right here, plus as well. Cl's the same, it's negative, and this one's positive. You can once again see it in the periodic table. So basically on the left side, it is positive charge. On the very left, it's positive charge only, but a little bit to the left, second group, it's actually +2. And then on the right side, it's usually negative, as you can see the periodic table. So now we're going to see what kind of spectrums we have. So Cl is unique, it's only on the left side. 2 also, 2BO2, 2Br is different. Okay, 2Cl. So we have 2K right here. Is it presents on both product and ions on the left and right side. So we're going to cross that out because it's considered as spectator ions. So now you're going to write down the equation again without the spectator ions. And now we have the final ionic equation without the spectator ions. So this is basically how you do ionic equations. So once again, usually this type of question, I'm going to discuss this next week so that it also serves as a review. So we're going to do the work example, and then I'm going to try to solve this first, and then I'm going to explain it to all of you later next week. So chemists usually prefer to write ionic equations for precipitation reactions. So a precipitating reaction is a reaction where two aqueous solutions react to form a solid to precipitate. This is a unique reaction. For this equation, the method of writing the ionic equation can be simplified. All you have to do is write the formula of the precipitate as the product, and then write the ions that go to make up the precipitate as the reactants. It's kind of confusing, so we're just going to look at the work example right here. So an aqueous solution of iron 2 sulfate reacts with an aqueous solution of sodium hydroxide. The precipitate A precipitate of iron 2 hydroxide is formed together with an aqueous solution of sodium sulfate. So here we have the full balance equation. And now this is the ionic equation. Okay, so just to put it simple, since we're actually almost running out of time. Okay, hold on, give me a second. Okay, sorry about that. So basically the two reactants right here is to form a product. And the product has to be solid, so just like cross the aqueous solution out. So we are going to cross sodium right here, sodium right here. So that's why we are left with 2 OH. And then the SO4 right here. the sodium sulfate right here. Oh, sorry, I mean that's the sulfate. The sulfate right here. So I'm going to cross sulfate out and cross sulfate here out. So that's how we ended up with F iron 2 plus 2OH minus right here and FeOH2S. So that's how basically I end up with this. Just by crossing out this aqueous right here. Okay, so I hope you can understand. And here we have another work example. We're going to go through that next week. And it's also actually serve as a review as well. So we're going to discuss this in a little bit since we have still a few minutes before the class ends. So calculating the concentration of a solution. The concentration of a solution is the amount of solute dissolved in solvent to make 1 cubic decimeter solution. Solvent is usually water. There are 1,000 centimeter cubic decimeter. When 1 mole of a compound is dissolved to make 1 decimeter cube of solution to concentration 1 mole decimeter negative cube. So this is a formula concentration. This is basically the unit, and then this has formula of number of moles of solute, which is the unit mole, will be divided by the volume of solution, which is in decimeter cube. So we use the term concentration in dilute to refer to the relative amount of solute in the solution. A solution with a low concentration of solute is a dilute solution. If there is a high concentration of solute, the solution is concentrated. So it's basically just the opposite and vice versa, something like that. You can get the hang of it once you start learning more. So when performing calculations involving concentrations in mole decimeter cube, you need to change mass in grams to moles, change centimeter cube to decimeter cube. So I think we have time, right? Yeah, we have time just to discuss this work example for a while. So it's actually pretty simple. We're just going to use the formula that is stated previously above. So calculate the concentration in mole decimeter negative cube of sodium hydroxide NaOH is, yeah, this is basically the name of the symbol. If 250 centimeter cube of solution contains 2 grams of sodium hydroxide. So the amount value of sodium hydroxide is 40. So first of all, we're going to change the grams to moles. And how do we change that? We're going to divide 2, right here, the 2 grams. We're going to divide that by the MR value. So we have 2 divided by 40. We have 0.050 mole of sodium hydroxide. So after that, we're going to change centimeter to decimeters. So 250, you're going to divide that by 1,000. So we get 0.25 decimeter. So now we're going to calculate the concentration. As we can see, this is the formula. Number of moles of solute will be divided by the volume. So we have the number of solute right here, which is 0.050. We're going to divide that by the volume, which is 0.25. And that's how we get 0.20. Don't forget the unit. The unit is mole decimeter negative cube. So do you have any questions so far about
No,
the today's class? No. Okay, so if none of you have any questions,
no.
and yeah, okay, so if none of you have any questions, I'm going to end the class now. And I think if some of you have any other class or other things to do after this, you can just go ahead. I'm going to stop sharing my screen, and I'm also going to stop the recording.